All right, you survived till the second video. We got a couple more for you, and then a couple more after that. And yeah, hope you're ready for some math. So we are going to start by introducing some properties from the book. I'm not going to copy all these properties down into my notes. You can pause the video and do so, or you can go to the book directly and do so from there. And the reason why I'm not going to do that is because all of these properties are just properties of addition, right? Sigma notation is just adding things up. So all of these properties are the same as any other property that you know of with addition. So I'll show you the properties. All right, you should see them right here. So if I add up a bunch of a constant that has nothing to do with i's, it's just, well, how many turns are there times what it is. Like I said, I'm not going to write it down, but like all of these, they make a lot of sense when you write them down. So this is just plug in the first I, but there's no I. Plus the second I, there's no I, so we're not plugging in 2 anywhere because there's no I. Think about functions, constant function. Plus the third one, plus all the way up to the nth one, but every single one is just C. Well, how many C's are there? There are n C's. Well, how do we write n C's added together? North Carolina. And so that's what all these properties are. Okay, so if you'd like, it's a good idea to copy them down. We can use them later on. I don't want to spend time going through them individually. I have a lot of faith in you. I do want to comment on number 5, though. So I'll leave a little space. 1, 2, 3, 4, 5. Okay, that's a 5. It kind of looks like a 3. So number 5 is a little interesting. It's a little funny, I think. So if I'm adding up the first n terms here, something that we can do is we can just add up the first m terms and then add the rest. So if we start, I equals m plus 1, we add up from 1 to m, and then from m plus 1 all the way to n. These are the same things, and this one we'll be able to use quite a bit in these problems. And again, you can check the examples video. There will always be a selected homework problem video at the end of every section in this class. You can see more of examples in those ones of me using these properties, but they're basically self-explanatory once you write them out like that. And I don't want to take your time doing that, or my time, to be perfectly honest. So I want to show you guys interesting, more difficult things, the stuff that you probably can use me more effectively for. All right, example 2. Let's do a little proof. Prove the second one. I think it's the second one. That the sum of the first n terms of some constant times some sequence. Talk more about sequences in Calc 3, I believe. Anyone's taking that. Prove that this is equal to C times the sum from I equals 1 to n of a sub I. Now, you don't have to freak out. I know I said the P word, but proving this is just starting with one side and saying, hey, look, this is all equal to each other. This is all equal to each other. Voila, it's equal to the other side. That's all we're doing here. So let's start with the left-hand side. Left-hand side is the sum from I equals 1 to n of some constant times some a sub I. It doesn't matter what it is. Well, that's sigma notation. Let's write out what that actually means. Also, it's great practice right now. If you wanted to pause the video and write out what this is and see if you can eventually get to this right-hand side, that'd be a really good thing to do right now. If you pause the video like now, or you can watch on. So remember, sigma notation says, all right, well, what's the first I? First I is 1. So we get C times when I is equal to 1. And then we add it to the second I, which is C times, well, now I is 2. And I just keeps counting up, and we just keep adding and adding plus c times the third I, which is a sub 3, and all the way on until the last one, which is some constant, times a sub n. Look at where we're trying to go. Anytime you're trying to prove something, look where you're at and look at where you're trying to go. We're trying to prove that a c on the inside is basically a c on the outside. So let's factor. That's what factoring is all about, taking things out to the outside. Factor out a c, and then we're left with a1 plus a2 plus a3 plus, oh, here it's all coming into play. Well, what's this? It's just that. Now we did it. That wasn't too bad, right? I think all of you could do this for all of these properties. Might be on a quiz. Ooh, that could be fun. Who knows? So this is just c times the sum of I equals 1 to n of a sub I, which is the right-hand side, just like we wanted to show. Check, check. Good. And that's how we can do it. Now, there are some other useful formulas that I'm going to write down because they are not self-explanatory. You will want these in your notes for the homework, for the quiz. You'll want these down. And at least the first one, it can be fairly easy to see where it comes from with a little bit of work. The later ones are a little bit messier. So if I just want to add up 1 plus 2 plus 3 plus 4 plus 5, etc., sum up the first n terms of I, that's going to just be how many total terms are there times one more than that, all over 2. And there's this very famous story that of dubious truthness, there's a better way of saying that, about Gauss, the famous mathematician and many other things, about doing this when he was a kid. And basically, right, if you want to add up all the numbers from 1 to 100, well, you just add the first and the last. That's 101. 1 plus 100. And then you can add the ones a little inside. 2 and 99. Well, that's also 101. Plus 3 and 98. Well, that's also 101. And you just get a bunch of pairs of 101, and then it turns out that this is basically what you're doing. Okay? But we're not going to do that now. And then there's one for squareds. And there's one for cubes. And I'm going to be honest with you, I don't have the squared or cubed ones memorized either. So good thing it's open notes. So this is going to be n times n plus 1 times 2n plus 1. So if we just square 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to some number n squared, well, the result just depends on how big n is. And whatever n is, we just plug it into that formula and we can get that sum. And then this one is weirdly kind of nicer. This cubed one is going to be n squared times n plus 1 squared all over 4. So these are nice handy dandy little formulas. Make a note of them, use them, keep them accessible in your notes. All right. Now let's do some examples, and that's all for this video. I like these examples. I don't want to spoil it though, but just get ready to be excited, all right? Can you do that for me? Get ready to be excited. Evaluate. I'm getting too excited. It's just sigma notation. This has got to be the least interesting section of the whole class. It's important, but I mean, it's mostly just notation, right? And then we get into the really cool stuff. But I'm still excited, so that's a good sign, right? Evaluate the sum of I minus 3 squared, where I goes from 1 to 2, all the way to 200. Now you have two kind of straightforward ways of starting this, two options. One, you could write this out. Say, well, the first one is when I is equal to 1. That's going to be 1 minus 3, negative 2 squared. All right. Now the second one, 2 minus 3 is negative 1 squared, plus the third one, and you can do this 200 times. Or if you didn't want to do that 200 times, it would work. If you didn't want to do that 200 times, what you could do instead is write this with summation notation and see if we got any nice handy dandy properties we can use. That's my recommendation. We could have a race, all right? You can pause the video, you can do it one way, I'll do it the other way, we'll see who wins. Yeah, if you use a computer though, that's not part of the, I'm not racing a computer. Okay, so we write this with summation notation. We start at 1 and we go all the way up to 200. We're adding I minus 3 cubed. So we say, okay. We have any formulas? Yeah, Jason just gave us a formula. He gave us a formula for something squared. We know that. For I squared. We don't have anything for I minus 3 squared. So what we're going to do is we're going to rewrite this as some kind of sum of I squared. And there's a couple of different ways of doing this. All right, so one of the ways would be to FOIL this out. If you FOIL this out, you're going to get I squared minus 6I plus 9. And then we can do each one of these individually. I think that's probably the most straightforward way. Option 1 would be to FOIL it out and write it as the sum, I goes from 1 to 200, of I squared minus 6I plus 9, and then use the properties from there. The sum of I squared we can do, factor out a 6, sum of I we can do, and the last one we can do as well. I think this is the most straightforward, but I don't think it's the easiest. Easiest would be to re-index. All right, but again, this blue option is really a great option too. All right, but the green option is going to be a little quicker. So here's my claim. My claim that is that if we just fill in the blanks correctly, we have the sum of I squared right now. Why is that? Because let's look at the first term here. What's the first term here? First term is when I is equal to 1, it's negative 2 squared. Okay, that's negative 2 squared. And then the next term is negative 1 squared, plus all the way to the last term, which is 197 squared. So we can just change this first term and this last term and now just write it as an I squared. Or do the blue method. Well, the first term is negative 2. And the last term is 197. So we've now taken this and translated it into something that's much closer to one of our properties. It's much closer to us being able to use this formula. But we can't use it yet. There's another step. Because this formula is only from 1 to n. And ours is going from negative 2 to n. So really, if this thing right here were a 1, we'd be good to go, but it's not. And that's where property 5 comes into play. Property 5 comes into play. We can split it up. Right? We have negative 2 up to 197. Well, let's just take out the first couple terms and then write it as the sum from 1 to 197. And then we can make things a lot easier on ourselves. Right? Because I know this is just negative 2 squared plus negative 1 squared plus 0 squared and then plus 1 squared, right? This is an intermediate step you can keep or get rid of if you want. And now we know that this red area is just exactly what we want. Right? This red thing is just the sum from I goes from 1 all the way up to 197 of I squared. And we have a formula for that. So again, the blue method is one way, maybe a little bit more straightforward. The green method is a little trickier, but it's going to be less work if you can see it. So I want to show you two different ways of approaching this problem. And you might say, well, Jason, well, what about this? What about it? I know what -2 squared plus -1 squared plus 0 squared is. I can do that in my head. That's 4 plus 1 is 5. There we go. 5, I know what 5 is. That sum, I can use the formula. Right? We're summing from 1 to some number n of I squared. So let's use it. So this is going to be 5 plus, well, it's going to be n times, see, I already forgot. N times n plus 1 times 2n plus 1 over 6. And what is n here? 197. So we can just use the formula. So n, 197, times n plus 1, 198, plus 2n plus 1, 2 times 197 plus 1, all over 6. And just type that into a calculator and you should be good to go. All right, so let's type it into a calculator. We had 5 plus 197 times 198 times 197 times 2 plus 1 all over 6. It is 2,567,900. Two, 5, 6, 7, 900. So you could have counted that manually, or you can use summation notation and some little tricks and formulas to get it all put together. Again, both of these methods would have worked. Your choice. Let's do another one. This video is not 13 minutes. All right, let's do another. Let's do part B. I want you to now add up sum I equals 1 to 6 I cubed minus I squared. All right, this one you really could just add them all up manually. It's only 6 things to add up, but let's get some practice. Okay, you could do this manually. Let's get some practice. We have a formula for I cubed. We have a formula for I squared. It's already starting from 1, so that's nice. Let's use those properties that I ran away from. These properties over here that if you have subtraction, you can just subtract the sums individually. So by that property, this is going to be that, hold on, I'll be really good. That's property 1.4. By 1.4, that's going to be the sum from I equals 1 to 6 of I cubed minus the sum from I equals 1 to 6 of I squared. And now, well, we have a formula for this guy, n is equal to 6. And we have a formula for the other guy, where n is also equal to 6. And right, these should look exactly like those formulas in this box. Just instead of n, we have an actual number. So for cubed, it's going to be n squared times n plus 1 squared over 4. N squared times n plus 1 squared over 4, where n is 6, minus n times n plus 1 times 2n minus 1, 2n plus 1. 2 times 6 plus 1 is 13. All over 6. Now we can just simplify and add it all together. You can use a calculator, or you can do it by hand. 6 squared times 7 squared times 7 squared divided by 4 minus 6 times 7 times 13 over 6. 350. And if you added these all up manually, 1 cubed minus 1 squared plus 2 cubed minus 2 squared plus 3 cubed minus 3 squared. Actually, that shouldn't take that long, right? 1 cubed minus 1 squared plus 2 cubed minus 2 squared plus 3 cubed minus 3 squared. 4 cubed minus 4 squared plus 5 cubed minus 5 squared plus 6 cubed. All right, this took longer than I wanted it to. Hey, it's 350 as well. So again, this one you really could just do directly, but it's good practice. All right. Let's do the last problem of this video, and then you can do some more problems and get some more practice. Take a breather. Actually, it's a video. You can pause it and you can breathe whenever you'd like. You have my permission. In fact, I highly recommend you continue breathing. Let's add up the function f of x equals x cubed. And we're adding it up when x is equal to 1 and when x is equal to 2, all the way until x is equal to 10. Huh. All right. So what is that asking us to do? Add this function at these certain values. So it's wanting us to do, all right, f of 1 plus f of 2 plus ... plus f of 10. That's what it wants. Well, we can write this in summation notation if we want. I is starting from 1. It's going all the way up to 10. We're adding the function value. You don't have to write it this way, but I'm going to write it this way. We're adding up the function value at that I value. Adding up a whole bunch of function values all together. Well, we know what that function is. The function, right? This is just, well, we know what f of x is. So f of I is just replacing the x with I. We get I cubed. It's evaluating functions. Pre-calculus. Oh, now we can use a formula again. It's what? N squared times, I don't remember. N squared times n plus 1 squared over 4. So n squared, n is 10. Remember, we are going from 1 to 10, so it's in the right format. Times n plus 1 squared, all over 4, that's 100 times 121. All over 4, that's, hold on, I can do this. That's 60,500 divided by 2. That's 30,250. Let's use a calculator. 10 squared times 11 squared all over 4. Oh, 3,025. Just like I thought. 3,025, just as expected. All right. Oh yeah, because it starts as 12,000. I was thinking about 121,000. All right, we're good. So there we go. So here's the time for the big reveal. I just tricked you guys. Look at what we just did. We're looking at a function. I've betrayed your trust. The cubic function, right? This cubic function looks like this. We're looking at this function between 1 and 10, and what are we doing? We're taking, well, we can count from 1 to 10, right? 5, 6, 7, 8, 9. 1, 2, 3, 4, 5. Well, what's the width of each one of these intervals? The width of each one of these intervals is 1. And the height of this first guy is the function value at 1, right? The height of this first rectangle is just whatever the function value is. So this is 1 times 1. That's the area of a rectangle. And then over here, this is 2. How high is the function? F of 2. 2 cubed. That's another rectangle. And then the third number was another rectangle. The fourth number was another rectangle. The fifth number, another rectangle. Sixth number, another rectangle. Seventh number, another rectangle. Eighth, another rectangle. Ninth, another rectangle. 10th, another rectangle. We just added up 10 different rectangles. We just approximated the area under the curve. And we didn't even know it. And that's what we're going to be doing for the rest of this section. We want to approximate the area under the curve. Why? I'll show you why later. There's still some exciting things that are going to come into play here. And how we're going to do that is by doing this sort of a thing. Okay? We can approximate it pretty easy with rectangles and what we know about functions and these properties that we've talked about. And now this isn't a particularly good estimate. Like, look at all this extra area we're getting, right? But as we add more and more rectangles that get smaller and smaller, doing more of something that keep getting smaller, as we get some sort of limit, might I say, limit, remember your limits from Calc 1, we're going to approach the actual area. And that is a process that we'll eventually call integration. There, I said it. That's what we're doing in chapter 1, integration. This is where it all comes from. Adding up a bunch of rectangles, which is really just adding up a bunch of things. And that's what we're starting here in 1.1 with. Good luck, and let me know if you have questions.